Number 23 from chapter 8. This is the one about the Ferris wheel. We're supposed to figure out how much heavier or lighter the person feels as they reach the top or the bottom of the Ferris wheel, which is a familiar sensation to anybody who's ridden a Ferris wheel. You tend to feel a little bit lighter as you're rounding the crest at the top and a little bit heavier here at the bottom. Before we do this problem, though, let's review the 3 convenient formulas for calculating centripetal acceleration. So if you are moving in a circle, which means you've got a fixed distance from the center, that's the definition of a circle after all. You've got some speed, v tangential, and that speed could actually be changing. You could be speeding up or slowing down, but whatever the speed is at a particular moment, that's the speed you would use to calculate the centripetal acceleration at that moment. And here's that formula. We tend to call that A sub r. It's centripetal because it points towards the center. And I just said that you could be speeding up or slowing down, and that's true. If you were, you would have an additional acceleration tangent to the circle. Right now, we're just talking about the component of acceleration, excuse me, towards the center. And we know that that is v squared over r. I'm just going to write v squared instead of v tangential squared. But these two things are the same, these two speeds. Now, you may recall there's a relation between angular quantities and linear quantities, like there's an angular velocity, omega. We can relate that to the tangential velocity with this formula. Tangential velocity, which I'll just call v, is r omega. R is the radius of the circle, of course. So we could plug that in here and find that the centripetal acceleration could also be described as r omega squared over r. Now, when we square everything inside the parentheses, we will get an r squared. This r downstairs cancels one of the r's upstairs, and we're left with r omega squared. So I'll put a box around these. These are equivalent ways of calculating the centripetal acceleration. Use whichever is most convenient. It depends on which information is given to you in the problem. If you know the angular velocity out at the outset, for instance, maybe it's given in RPM and you would have to convert it into radians per second. That's just one quick conversion. And then this might be the simplest way to proceed. It doesn't matter which formula you use, they would give you the same number. There's a third formula, however. Remember, for constant speed, speed is distance over time. So if you're in uniform circular motion, you're going around at a constant speed, the distance around the circle once, of course, we call that the circumference, and we know that that's 2 pi r. And the time it takes to go around once is typically called the period, t. So we could then plug this into our more commonly used formula, v squared over r. And I'll just put dot, dot, dot. You should check this. Go ahead and square that all, divide by r. Another way of writing the centripetal acceleration is 4 pi squared r over t squared. See how the pi is squared, the r is not? Yeah, I'm checking that in my head. That all seems to work. Or it seems to work out. Okay, so you've got 3 different formulas. I have this memorized now after having seen it so many times. You may have trouble memorizing all 3 of them. Remember, you don't actually have to memorize all 3. You really just have to memorize one and understand this relation and this relation to get the other 2. If you want to memorize them, go for it. That's probably the easiest. Well, once you have memorized it, it's the easiest way to proceed with problems because you don't have to go through this step each time. Okay, so let's tackle this next problem using one or more of these formulas for centripetal acceleration. Okay. Well, this is chapter 8 after all, which is about the dynamics of circular motion. Let's start with the person at the top. What are the forces on this person? Of course, gravity is pulling down. And if you're sitting in a seat, most likely the seat is pushing up on your butt. So there's this force, which we may as well call the normal force, because it's perpendicular to the surface of the seat. So I will label them N and F, G. So let's do that at the top. This is just a sketch. Let's make a free body diagram now. And I am purposely making the normal force shorter than the gravity force. So the seat pushes up, gravity pulls down, and the circle looks like that. When it comes to the dynamics of circular motion, remember, we've got three special axes along which to apply F equals ma. Hopefully you've had plenty of practice with this now. We've got the T, R, and Z axes. Now in this problem, nothing interesting is happening along the T axis, and certainly nothing is happening along the Z axis. All we're really interested in is what's going on along the R axis. And I think it's safe to say that every circular motion problem that you do will require you to write the R equation. You may not have to write the T equation. You almost never have to, well, I was going to say you almost never have to write the Z equation, but that's not true for banked roadway type problems. So any of those three equations may be required, but the R equation, almost always necessary. So we'll say the sum of the forces along the R axis is mass times the so-called centripetal acceleration. Okay. And which ones get the plus signs? You look at all the forces along this axis that passes through the center of the circle. The one that points towards the center gets the plus sign. So gravity gets the plus sign, and the normal force gets the minus sign. And now we go ahead and plug in the formula for centripetal acceleration. I guess I'm not doing that yet because I want to decide which of these would be most convenient. And they're asking us for the person's weight. And remember, the way your book does it, weight is really the support force or normal force on your body, which determines your perceived weight, like how heavy you feel. When you're in an elevator that's accelerating upwards, during that time, you feel heavier because the floor of the elevator actually is pushing harder on your feet. So weight really corresponds to normal force, not mg. Mg would be your weight if you're just standing on the ground and nothing's pushing down on you. Or if you were in free fall, that would be the force on your body due to gravity. So we're using the word weight in a different way than just mg. It refers to the normal force. Okay, so since that's what we're interested in, we have to solve for n. And I would put the n over here and then take this term, put it on the other side, and factor out m. So this is m times g minus the centripetal acceleration. So we already see that if this number is non-zero, if we plug in some positive number here, we're actually subtracting a term from mg, which means that the person's going to experience less weight. They will feel a little less heavy than they typically do. And now I'm looking at the statement of the problem, number 23. What we're told is that the radius of the big wheel is 15 meters. Okay, so we know the R in v squared over r. And we're told that the person on this Ferris wheel estimates it takes about 25 seconds to go around the loop one time. It should be a rather long time, right? If you whipped around every second, that would be a terrifying Ferris wheel and it would probably injure you. So they tend to move pretty slowly. The thrill comes from the height, not the acceleration. And Ferris wheels are not famous for their accelerations. Okay. So since I know the period and I know the radius, I'm thinking this would be the most convenient formula to use. I could plug R and T into this formula to first find the tangential speed as the passenger goes around, but it would be more direct just to plug the numbers that I have into here. Okay. And I'm going to do this a slightly different way from the way your solutions manual does it. Watch this. The centripetal acceleration is 4 pi squared times the radius of 15 meters divided by 25 seconds squared. And we can see the units come out right, meters per second squared. Let's plug this into the calculator and see what we get. 4 times pi squared times 15 divided by 25 squared. And I get 0.947 meters per second per second. And then I'm going to convert this into G's. What multiple of the free fall acceleration is this number? So times 1G for every 9.8 meters per second per second. Divide by 9.8. So this is, I suppose I'll round to 0.1. This, I'm getting 0.0967. I'll just call that 0.1 G. And the reason I'm doing it that way is it makes it easier to answer the actual question that was posed, which is, what's the ratio? I think they said, what's the ratio of your perceived weight at the top of the ride versus your weight when you're just standing on the ground? So I plug this 0.1 G in now for the centripetal acceleration here. And we've got G minus 0.1 G. Well, 1 G minus a tenth of G, that's 9/10 of G, or 0.9 G. So the normal force is 0.9 mg. And of course, mg is what you would weigh if you were just standing on the ground, right? If this is used standing on the ground, you've got the ground pushing up on you and gravity pulling down. Those two forces have to sum to zero since your body is in equilibrium. So now the answer is staring us in the face. When they say, how does your weight at the top compare to your normal weight, so to speak? It's 90%. So you weigh 10% less at the top of the ride because your centripetal acceleration at the top is 10% of G. Super sensible. And now we can look at the dynamics at the bottom of the wheel. At the bottom, once again, here's the normal force pointing up and gravity pointing down. And I forgot to finish this thought earlier. So in part A of the problem, I deliberately drew N shorter than the gravity force because I know that the net force must point towards the center. Down here at the bottom, the same reasoning applies. Since the net force must point towards the center, the arrow for N must be longer than the arrow for gravity. So we can see just physically why you're going to weigh a little bit less than mg at the top and you'll weigh a little bit more than mg at the bottom. Ooh, excuse me. So if I want to make a free body diagram, it's kind of unnecessary, but this particle represents the passenger at the bottom. Here's N, and here's mg. Is that a text message? Somebody loves me. Okay, just like before, the only interesting axis here is the r axis. Sum of the forces in the r direction is mass times acceleration in the r direction. And I'd like to interject a quick point that used to confuse me, that doesn't get addressed very often at this level of mechanics. So like, you know, your first semester of calculus-based mechanics. This equation, F equals ma along the r axis, if you're going to plug in v squared over r or r omega squared or the third formula, this equation is really only correct if you're moving in a circle of fixed radius, which is kind of redundant because if you're moving in a circle, of course, your radius is fixed. So I'll just say it's only true for circular motion. If you would like to use polar coordinates for non-circular motion, like if you're spiraling out of a circle or just doing something arbitrary in the r theta plane, then this equation really is not correct if you just put v squared over r in. You'd have to have additional terms. So it only works if you're in circular motion. Now, fortunately in this class, that's all we're doing. So you can always just default to plugging in v squared over r. Okay. Remember, on the left side of the equation, the forces that point towards the center get the plus sign. Now, previously, it was gravity that pointed towards the center. Now, N is the one that points towards the center. So sign is important. Now it's N minus mg is m times acceleration. And when we solve for when we solve for N as in Nancy now, put the mg on the other side, we see that those two terms add. Factor out the mass. Now we get this, which is different from before. There was a minus sign. So if you're not observant of which forces get the plus sign, your result will not come out correct. Now, let's save ourselves some work. We don't need to recompute a sub r because whether you're at the top or the bottom in this problem, you're still moving at the same speed and the circle still has the same radius. So we already know that the acceleration is 1/10 of g. And that means the normal force at the bottom will be m times g plus 1/10 of g. In other words, 1.1. 1 plus 1/10 is 1 1/10. Okay. In other words, you weigh 10% more at the bottom. So to summarize, if you're on a Ferris wheel and the acceleration of that Ferris wheel is 1/10 of g, the centripetal acceleration, then at the top you weigh 10% less than you normally would, and at the bottom you weigh 10% more. And it's easy to generalize. If this period were shorter, if you were whipping around faster, maybe your acceleration came out to be 0.2 g's, in other words, 20% of g. So if your centripetal acceleration is 20% of g, you would weigh 20% less at the top and 20% more at the bottom. So it's good to have those rules in your head, that kind of summary of the physical content here. But for this class, the most important thing is to know how to correctly apply Newton's second law for circular motion. That's really the place that you want to start. Numero 26, different setup, different scenario here, but extremely similar problem-solving process, which is true for many of the problems in this chapter. We're told that there's a ball on a string. This is a classroom demo, so it's tied to the ceiling here. Somebody pulls the ball to the side, releases it, and it passes through its bottommost point with a particular speed. We're given how long the rope is here. And we're supposed to figure out what the tension is in this rope at the moment the ball passes through its lowest point. What is that tension? We could probably find the tension at anywhere along this circular trajectory, provided we had the angle here. Now, they don't actually give us the angle to which the ball is raised, but we don't need it because they already told us how fast the ball is moving at the bottom. Now, you'll notice when we go to draw forces, we're interested in the tension when the ball is here. The tension would point straight up. Gravity would point down. And again, I made sure to draw T longer because I know that the net force must point towards the center. Okay, now they told us not the mass of the ball, they gave us the weight in newtons. Now remember, weight, now it's getting complicated because in the previous problem, we used the word weight to mean specifically normal force. But right now it's being used to mean the gravity force. So, you just have to go by the context. You have to be flexible in your understanding of what the word weight means exactly. Right now, we just mean the force of gravity. Well, that's typically mg. Now, I don't think we're going to need the mass. We might. We'll find out in a moment. But if we did need the mass, do you see we could just divide by g on both sides? Right? Divide by g, divide by g. Of course, g cancels. So if we took the 100 newtons and divided by 9.8 newtons per kilogram, we would know the mass of the ball in kilograms. It's not always necessary to do that, though. Okay, so I'm using W for weight. Let's do a free body diagram right here. Put the arc of the circle. It's not really necessary, is it? It's basically already drawn. Tension, weight, and we'll start with Newton's second law along the r-axis. The sum of all the forces along the r-axis must equal mass times centripetal acceleration. And we're trying to find the period. No, excuse me, not the period, the tension, T. So in this instance, capital T represents tension. That's why some books put F sub T for tension force, so you don't confuse T for period. Okay. Tension is the force that points towards the center. That's why it gets the plus sign. Gravity points away from the center. All right. And how should we proceed here? It looks like I'm going to factor out the mass because I was trying to avoid calculating the mass, but I don't really see any way around it. We kind of have to. So the mass here, I'll just take that 100 newtons and divide by 9.8 newtons for every kilogram to find that the mass is 10.2 kilograms. I'm sorry, you couldn't see that up here. 100 divided by 9.8 is 10.2 kilograms. Now I can plug that in here, and I can also evaluate the centripetal acceleration. So which of these three formulas would be most convenient for this particular problem? Well, the length of the rope is actually the radius of the circle. Do you see that? The radius of the circular arc traced out by this ball is determined by the length of the rope. So that's the 4.5 meters. So I know the radius and I know the speed. That means it would be easiest to just use this one directly, v squared over r. All right, here's how I will do it in my calculator. Let me first do the quantity in parentheses, and then I'll hit equals before I multiply by the mass. So v squared over r would be the 5.5 meters squared divided by the radius of 4.5 meters. Okay, now my calculator knows order of operations, so then I can go plus 9.8. And then I hit equals first to evaluate everything in the parentheses, because I don't like messing with parentheses on a calculator. Then I multiply by 10.2. And I find that the tension is 168.5. What's with me in the eighths? There we go. Newtons, which you'll notice is greater than the weight, right? The ball only weighs 100 newtons. So why does the rope have to have more than 100 newtons of tension in it at the bottom? Because not only must the rope support the weight of the ball, it must also provide the centripetal acceleration. So the tension has to be even greater than the weight, meaning mg, of the ball. Number 30, this is a good one because it ties together several concepts. We've got three different vehicles. I think they're all identical. They're all driving at 25 meters per second, which is almost 60 miles an hour. And for each of these cars, there's some reason why they need to hit the brakes. But the wheels lock, and so the car skids. Remember, controlled braking, where the wheels roll to a stop in a controlled fashion, that takes advantage of static friction. If you're skidding, the rubber is actually sliding over the road. You're talking about kinetic friction. And we know that kinetic friction is proportional to how hard your tires are pressed into the road, otherwise known as the normal force. So if we can figure out the normal force on the vehicle in each of these three cases, we will know how much kinetic friction there is on the car, and that will tell us how quickly the car can slow down, because ultimately, like let's take car B for instance, if it's traveling in this direction and slowing down, that's due to a friction force in the opposite direction. So the greater the friction force, the greater the acceleration. Okay, car A. Well, car A is driving on a section of the ground that's flat. So this car is not in circular motion. And an important point to realize is that a particle in circular motion does not actually need to trace out a full circle in order for it to qualify as circular motion. In fact, most of the time, something in circular motion does not trace out a full circle. So even if this car is only momentarily traveling, along an arc of a circle, that still counts as circular motion. So for car A, I guess I could draw the forces I see up here as well. Gravity pulls down, the ground pushes up, that's what we call the normal force. And because the car is braking, there's a backwards kinetic friction force. So right here, you know what? This is a little too bold for this page, so I'm going to switch back to the pen. Normal force up, gravity down, I'll call that mg, and friction backwards. Okay, now for this part of the problem, let me go with a coordinate system like this, x-axis to the right and a y-axis up. Now I know there's no reason that this car should be accelerating vertically. It's not lifting off the ground or falling into the ground. So I can say that the car is in equilibrium along the y-axis, and that means n minus mg is 0, this is what tells us that the normal force on the car is simply equal to the gravity force. The only way to know for sure what the normal force is to write F equals ma along an axis in the normal direction. That's the only way to know for sure what the normal force is. Now that we know what the normal force is, we can say that kinetic friction is mu times the normal force. Well, that's going to be mu times mg. So we can now look at the x-axis and figure out what the acceleration is going to be. So the net force in the x direction is mass times acceleration in the x direction. I only see one force horizontally. That's the kinetic friction, which points in the negative x direction. So negative Fk. Well, Fk is this. So I'm just going to substitute directly. This is the kinetic friction. You see that the masses cancel, and we find that the acceleration parallel to the ground, it is parallel to the ground, you could say tangent to the ground, is negative mu g. And I think all we're doing in this problem is calculating the acceleration for these three situations. Yeah, now they ask, what's the tangential acceleration of each car? We don't typically think of this as being tangent to the ground, but it is. The friction force is tangent to the ground. So we've just answered the question for car A. Now let's think about this physically. Remember, whichever car is being pushed or pressed into the ground the hardest will experience the greatest friction and hence experience the greatest magnitude of acceleration. So which of these cars is pushed hardest into the ground? Because of our work in the Ferris wheel problem, for instance, hopefully you see that the normal force will be greater for this car as it's bottoming out, because the ground down here, not only does the ground have to continue supporting the weight of the car or the gravity force of the car, it has to accelerate the car towards the center. So the ground has to push even harder. And it's easy to imagine this, right? If you were a person running down this embankment, you would feel heaviest at the bottom and you'd feel a little lighter on your way up. So I expect the normal force here to be less than usual, and I expect the normal force here to be greater than usual. So now we go to part B. Here's my dot to represent the car. And I still have a normal force up, but I'm going to make that arrow longer now. Gravity down, friction back. N has to be longer so that the net force points towards the center. And now we have to pick new names for our axes. Here I just went with X and Y because this car is not in circular motion. Car B is in circular motion. In fact, the circle it's tracing out looks like this. So this axis, instead of calling it the y-axis, I really need to call it the r-axis now. We're using that special TRZ coordinate system for circular motion problems. And this axis would be the tangential axis. You see how this direction is tangent to the circle. We don't need the z-axis for this problem. So sum of the forces along the r direction is equal to mass times acceleration along the r direction. Now they gave us the speed, and you know what? We also know the radius. So I'm going to look at the problem here. Number 30 says that the radius of curvature is 200 meters. So this is a very large circle. It makes sense. You wouldn't be driving in a tight circle on a normal runway. So that means I should just use v squared over r. That would be the easiest. Now, n is towards the center. See how the center of curvature is above the car? So n gets the plus sign. Gravity gets the minus sign. And when we solve for normal force, we do in fact find that it's greater than mg. We're adding this term. See, we've got two accelerations in here, the free fall acceleration and the centripetal acceleration, and they add in this instance. That might be surprising because the arrows point in the opposite direction, and yet the two accelerations add. So I wouldn't try to reason your way through these problems like just using your intuition. Some of you probably have some pretty powerful intuition about a lot of this stuff, but the safest thing is to start with Newton's second law. You can't go wrong with Newton's second law, unless you're talking about subatomic particles traveling close to the speed of light. Then it may not work so well. But for now, this is the best tool you've got. And I'm just going to leave that as is, or should I go ahead and calculate that? Hang on a second here. Yeah, so we do need to evaluate this numerically here. Since we're dealing with rubber on probably asphalt, they're suggesting that we go with a coefficient of just 1. That's fairly high for kinetic friction. So 1 times 9.8. So this car A slows down at 9.8 meters per second. We'll plug in numbers here to get an actual value for the acceleration for car B. Well, the normal force, are we going to need to know the mass of the car? No, they didn't give us the mass, which tells us that we don't need it. So we'll continue here on another sheet of paper. Let's kill another tree. It's good for the economy. Now we go to the axis tangent to the circle. Now, usually the positive direction for the t-axis is taken to be the direction of motion, and the friction points in the negative direction. So I'll say sum of the forces in the tangential direction equals mass times acceleration in the tangential direction. So this is linear tangential acceleration. The units are meters per second, not angular acceleration. Okay, I'll write negative FK. The minus sign is there for the reason I just described. FK is the magnitude. And we use this fact, always calculate kinetic friction as being proportional to normal force. That's why we had to do the r-axis first. The r-axis tells us how strong the normal force is. We can then plug that into the expression for kinetic friction to determine the tangential acceleration. So negative mu k times m quantity g plus v squared over r. Now you see why we didn't actually need to know the mass of the car. It cancels. All right, mu k is 1, so we don't even need to worry about that. Let's figure out how much greater this acceleration is. I'll evaluate the centripetal acceleration first. We're going 25 meters per second. Square that, divide by the radius of 200 meters. So 3. That's a modest term next to the 9.8. I'll add that to 9.8, and there it is. So that's almost 13. This car slows down at a rate almost 30% greater than the rate at which this car can slow down. Okay, that's kind of interesting. If you're bottoming out, or if you're driving through the bottom of a embankment, I'm not sure how to, a circular section of roadway, you can actually brake more effectively. You can slow down at a greater rate. Why? Because, I was going to say, because your car is being pressed harder into the road. But it's not necessarily that, because you could put more people into the car, and that would also press the car harder into the road, but then the car is more massive. So this is fundamentally different, I think, than just like piling more weight. You see what I'm getting at? Like, if all you have to do is increase the normal force, couldn't you just put more people in the car and you could brake more effectively? But I think you would find that the mass cancels out in that instance. So it's really about the fact that we're in circular motion. I've never tested this in real life, but it'd be interesting to see if the difference is notable, or excuse me, noticeable. Like if you're really familiar with your car's handling abilities and its braking capabilities, will you notice that you can brake over a shorter distance if you're at the bottom of a curve? Of course, as you brake, you slow down, and the slower you go, the weaker this term is. Moving on to C. Okay, we've got a normal force still, but we know from experience it's going to be a little less than it was before. Gravity has to be greater so that the net force in the R direction is towards the center, and then friction still points backwards. Let me do my little free body diagram. The circle looks like this. Normal force, gravity. Make that a little longer. I'm not looking for the appropriate length on exams. It's nice if you can include that, but I'm not going to take points off if you didn't draw this arrow longer, for instance, just as an example. Can we be smart about this? Because a lot of the work's already been done for car B. But just to be careful, FR equals MAR. Now, which of these forces gets the plus sign? Gravity is the one that points towards the center. It gets the plus sign minus N. Okay, now when we solve for N, we've got G minus V squared over R. Everything else is the same. When we go to apply Newton's second law along the tangential direction, we would write the same equation that we did previously. So I don't need to repeat that. The only difference is this plus sign is now a minus sign. Remember that? So the acceleration in the tangential direction, I'll put dot, dot, dot to indicate that we've kind of skipped over those steps, is negative mu times G minus, and I've already forgotten exactly what this was, but do I really need to do that? Couldn't I, let's see here, if this is 12.9, that's, I was gonna subtract 9.8 and figure out the difference, and this time, whatever, that's making it more complicated than it needs to be, so 9.8 minus 25 squared divided by 200. Okay, significant reduction. Don't forget the minus sign, meaning slowing down because of the way I set up my coordinate system. Okay, so it does make a big difference, whether you're at the bottom of the hill, the top of the hill, or just driving on flat ground in terms of your ability to brake. Here's a fun one. We're supposed to investigate whether a person would weigh more at the equator or at the North Pole, or is there no difference? So let's not forget that the Earth is rotating about an axis. That axis, by definition, passes through the South and North Poles, and it takes roughly 24 hours to rotate once about that axis. Now, if you look at this person, yeah, they are kind of doing the do-si-do once every day. Their whole body turns, but they're not really moving in a circle. They're just rotating about an axis that passes right through their body. So it's like they're moving in a circle of 0 radius. This person, on the other hand, really is moving in a rather large circle. This person lives at the equator. So there's not much to say about this person, except normal force pushes up on them and gravity pushes down. So at the North Pole, that person's free body diagram is really simple. We just say N minus mg has to be 0 because I don't see any acceleration along the axis for this person. Okay, so you would just take their mass and multiply by the local free fall acceleration. And here's where this might confuse you. We've been using the value 9.80 all semester. 9.80 is actually what you're left with after you account for the fact that we're rotating. If you could stop the Earth from rotating, you would find that, especially at the equator, everything actually felt a little heavier, and things would fall towards the surface at a slightly greater rate than 9.80. It would be more like 9.82 or even 9.83. But let's not worry about that for now. Let's just pretend that if the Earth were not spinning, everything, no matter where you were on planet Earth, would fall towards the surface at 9.80. And that's really not accurate because the Earth is shaped, this is a gross exaggeration, but the Earth is squashed a little bit because of its rotation. It's called an oblate spheroid. This would be a prolate spheroid, but Earth looks a little bit more like this. Again, grossly exaggerated. And because of this non-spherical shape, the strength of the G field changes depending on your latitude. So even if 9.80 was the legit value, that number would not be constant at different latitudes. We're not worried about those challenges right now. So the difficulty with the shape of the Earth, the non-spherical shape, just forget about that. Okay, so we're going to pretend that G is 9.80 everywhere. Now, what about at the equator? Well, now you have to imagine that you're looking down on this circle. So here's the equator as seen from the North Pole. And the person living at the equator now, they have to go around and around once a day. Now, there's still a force on them that points away from the Earth, which we should call the normal force. Oops, That's terrible. But don't forget about the force of gravity, which points towards the center of the Earth. I won't bother labeling that there. So we've got normal force away from the surface, gravity towards the center. And I really should have made this one longer because remember, if you're moving in a circle, the net force must point towards the center. And now this is the R axis. You know, you could say positive R axis, positive T axis, Z is coming out of the board. For this problem, we really just need the R axis. So this person going around here, in this picture, they would be doing that here. That's their circle that they're moving in. Okay, so some of the forces in the R direction is mass times acceleration in the R direction. And since gravity points towards the center, I give that one the plus sign, n points away. And remember, we're trying to compare the person's weight at the equator to their weight at the North Pole. Weight is how hard the surface you're standing on pushes on you. That's n. So it would be m times g minus a sub r. And I think we should do the following. Let's calculate a sub r in terms of g, like I did in the previous problem. And then we can just write this result as some multiple of g, like 0.8 g or 1.2 g. We'll see what it comes out to be. That means I need some room on a sheet of paper here. I'm looking for some real estate. This ought to do it. Well, we've got three formulas, right? V squared over r omega squared, and 4 pi squared r over t squared. Which one would be most convenient? What do you know about planet Earth off the top of your head? Do you know the speed in meters per second of somebody through space as they revolve with the Earth, or rotate with the Earth, I should say? I don't think any of you have that number just in the forefront of your mind. Do you know the angular speed in radians per second? I seriously doubt that. You know that it's 1 revolution per day, but that's not SI units of radians per second. So we could convert that, we could convert omega into SI units, but we do know the period. So I think we should do it with this formula. 4 pi squared r over t squared, because we also know the radius. I'm giving it to you here. This is in kilometers. That's a good value for the average radius of the Earth. I say average because remember, the radius of the Earth depends on whether you're at the equator or the pole. Okay. Well, it's not really necessary to get this technical, but it actually only takes the Earth 23 hours, 56 minutes, and something like 4 seconds to rotate once. And astronomers have measured this time interval to even greater precision. They know the rotational period of the Earth out to the 1,000th of a second, maybe even more precise than that, because now we have atomic clocks and we can time it super precisely. And believe it or not, it changes from day to day. Sometimes the Earth spins just a tad faster. And I'm talking like 4.052, 3, maybe that last digit changes from one day to the next. So totally imperceptible to everyday senses, but with an atomic clock, you can detect it. So why would that happen? Why would the Earth, slightly speed up and slow down? I don't know the answer to that question. I'm sure it's got something to do with tidal forces from the moon and the sun. That's probably an interesting thing to study. Okay, so here's what I'm going to do. I'll convert this into seconds, the SI unit of time. 23 hours times, well, there are 3,600 seconds in every hour. 56 minutes times 60 seconds per minute plus the 4 seconds. You could have just used 24 hours times 3,600. That's precise enough. But I'll be a little more precise. This is how many seconds are in a day. Yeah, really, it's unnecessary because the other numbers in the problem are less precise, like the radius of the Earth. I'm getting confused here. Okay, here's where I was going to compute the radial acceleration. Let's do this. 4 times pi squared times a radius of 6,370 kilometers. So I need to raise that to the third, or times 10 to the third power. You can't see that. 6,370 times 10 to the third. Then I divide by that period in SI units squared. So 86 164 squared. Okay, 0.034, really small centripetal acceleration. Now, if you actually calculated the speed of a person through space by virtue of living at the equator, somebody living in Ecuador, for instance, they're really going fast through space. I forget the number, but it's definitely faster than you drive on the freeway, much faster. And yet, their centripetal acceleration is small. Why is that? Well, they may be going really fast, but they're making a giant circle, and it takes a whole day to do so. And acceleration, centripetal acceleration is v squared over r. Yes, it's a large speed squared, but you're dividing by an enormous radius. Earth is a very big ball of rock and metal. So it still ends up being this small 0.034. And now let me divide that by 9.8 to express that acceleration in g's. Look at that, that's 3/1000ths of a g, 0.003 g. So by doing it this way, I can go back to my equation here and write this as m times g minus 0.003 g. Well, what's 1 minus 3/1000ths? Wouldn't that be 0.997 g? I sure hope I did that right, or that would be embarrassing. So, whoops, forgot the mg. Again, you don't have to do it this way. You could have actually just plugged in 9.8, plugged in 0.034, and gotten the answer in newtons. That's fine, because we're actually told that this person weighs 75 kilograms. I like to do it this way so that the ratio is evident. So if you go to the equator, versus the North Pole, if you were living at the North Pole and then you go to the equator, your weight decreases by 3/1000ths of what you normally weigh, 3/1000ths. And since we have it as a ratio, we can easily translate that into pounds. Like, what if you weigh 200 pounds? 3/1000ths of 200 pounds. Look at that, 0.6 pounds. Let's just call it half a pound. Okay, so if you're an average to large size adult, you're going to weigh half a pound less at the equator. Is that even noticeable? Like, let's say you woke up in the morning near the North Pole. Maybe you live somewhere in Canada, like the very far north part of Canada, or Iceland. Yes, you're in Iceland. And then you take a transcontinental flight that same day, and by the evening you're in the equator or at the equator. Would you notice that you felt a little lighter? I don't think so, because there's a bunch of, your weight can fluctuate by at least a pound throughout the day. So, but that's one quick way to lose weight. You want to lose weight, go to the equator. So why do you weigh less at the equator? Well, I'll put it this way. When you live at the North Pole, gravity does one thing. It pulls you into the ground. That's it. And the ground has to push back. That's your weight. When you live at the equator, gravity has a different function. Some of that gravity is needed to provide your centripetal acceleration. It's like you need something pulling you towards the center to keep you moving in a circle. Now, if the Earth were spinning faster, it could be that gravity was just strong enough to keep you moving in that circle, and you wouldn't even need the normal force. In that instance, you would be weightless. But as it stands, the Earth rotates really slowly. There's not a whole lot of centripetal force necessary. See how low the centripetal acceleration is? There's not much centripetal force needed to keep you moving in such a large circle at such a low speed. So it's like there's more gravity than is needed. So you still end up getting pulled into the ground, but not as hard as you would be at the North Pole. So I think you see what I'm getting at here. If you spun the Earth faster, you would be subtracting an even bigger number here, bringing your normal force down even lower. Carry that logic forward. There must be some speed at which v squared over r is large enough that this just goes to 0. In fact, you see what if a sub r was equal to 9.8, if the centripetal acceleration of this person living at the equator was in fact 9.8, 9.8 minus 9.8 is 0. That would mean you were weightless. So how could we make this number, which is currently 0.034, much higher so that it's 9.8? Well, the period would have to be shorter. If you make the denominator smaller, this entire number gets bigger. If the period of the Earth's rotation were small enough, the centripetal acceleration of a particle at the equator would be 9.8, and the normal force on that particle would be 0. So if you represent a person as a particle, they would be weightless. But that would be a very short day indeed, because the period of the Earth's rotation is the day, right? 1 day roughly. So that's an interesting problem. To understand how the Earth's rotational speed affects your weight. And I think I'll leave it there for this video. I'll come back with one more video likely dedicated to just a single problem, and that would be number 49, chapter 8, Randall Knight's Physics for Scientists and Engineers, 4th edition.